Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python Part 1. In this lecture, we are going to continue our discussion on how to train a neural network. Previously, we did a somewhat long digression on how to train logistic regression with softmax, but you'll see how that will become very useful in this lecture. To start, let's review what the central objects we have to consider are. First, we have our inputs x, which are of shape n by d. We then pass these through the first layer of our neural network, which gives us the hidden layer values z. This has the shape n by m. Finally, we pass z through the output layer of our neural network, and that gives us y. Y has the shape n by k. Next, let's consider our neural network weights. In the following lectures, we're going to use W and B for the input to hidden layer, and we're going to use V and C for the hidden to output layer. So W is a matrix of size D by M, while B is a vector of size M. V is a matrix of size M by K, while C is a vector of size K. By the way, in the previous lecture, we didn't use explicit bias terms, but in the following lectures, we will. It makes things a little bit more complicated, but it's necessary. Next, we can write down all the relevant equations for our neural network. And remember, our strategy is still the same as before. We want to build up our objective function, which is the log likelihood or the negative log likelihood. Then we want to find the gradient with respect to each parameter so that we can perform gradient ascent or gradient descent. Gradient ascent to maximize and gradient descent to minimize. So first, let's consider how we calculate z. Z is just sigma of W transpose x plus b. Now, keep in mind, we have multiple choices for sigma, such as the sigmoid, the tan h, or the rel u. But for the purpose of the following lectures, we'll mostly assume that we're using the sigmoid. Y is just the softmax of V transpose z plus c. Note that I've dropped any subscripts from x, y, and z for clarity, but you can assume that they all have two indices, one for the sample index and one for the feature dimension. Luckily, the objective we had doesn't change. We're still doing multi-class classification, so our loss is the categorical cross-entropy. We'll use the positive form of this, so it's the log likelihood, because again, if we don't, we'll just end up having to carry the negative sign over to every line, which can get tedious. Okay, so let's get right to it. We know the steps. Using the chain rule, we can find out which derivatives we have to solve for, and then multiply them all together. So let's start with V and C. Luckily, because we already did this for logistic regression, it's very easy to just copy what we had before. Remember that this is because we have composite functions. J is a function of y is a function of a is a function of V and C. At this point, we're not going to look at the input to hidden weights since they're a little more complicated, so you'll have to wait until the next lecture for that. In this lecture, we're going to continue to solve for the derivative of V and C. You'll notice that these equations take the exact same form as the equations for logistic regression with softmax. In fact, the first two equations are not just the same form, they are exactly the same. Therefore, their derivatives are also the same. Luckily, for the third part, which is just a linear transformation, is easy to derive. The derivative of ANK with respect to VMK is ZNM, which mirrors what we had before with logistic regression. And the derivative of ANK with respect to CK is just 1. Putting this all together, and using the results we found earlier, it's easy to see that these are the following derivatives for VMK and CK. As usual, we would like to vectorize these operations so that they are more efficient in code. Just like before, the gradient of J with respect to V is Z transpose times T minus Y. Unfortunately, there isn't really a convenient notation for the sum over one index of a matrix, which is what we have for the bias term C, so we'll just show what it would look like in NumPy. Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python Part 1. In this lecture, we are going to continue our discussion of backpropagation and talk about how to find the gradient of our objective with respect to the input weights W and B. Let's recap our neural network equations again along with our objective. First, we have Z, which is sigma of W transpose X plus B. Then we have Y, which is the softmax of V transpose Z plus C. Then we have our categorical cross-entropy objective. As before, it's convenient to have a variable to represent the activations at each layer, which is the value before we apply the activation function. Let's use A for the output, just like we did before, and let's use alpha for the hidden layer. So now our equations become alpha equals W transpose X plus B, Z equals sigma of alpha, A is V transpose Z plus C, Y is the softmax of A, and J is the cross entropy as usual. What makes this more difficult is that we now have many layers of functions. In other words, we have a function of a function of a function of a function with what looks like 5 levels. However, this shouldn't stop us from continuing, and we should just write down all the steps like we would normally do. So we want to find the gradient of J with respect to W and B. Luckily, each of these 5 derivatives are just the derivatives of the simple functions we looked at. So there's not much difficulty in the mechanical work that we have to do to take the derivatives. What is difficult about this is the conceptual part. In particular, we have to apply what is called the law of total derivatives. So as we've written them down now, these derivatives are wrong. So what's the problem? If you recall, there's this part where we transition from k prime to k. But remember what I said about dummy variables. They exist inside the summation, but not outside. The problem with this is, what happens to k? K appears on the inside, but it doesn't appear on the outside anymore. If you recall, k appeared on the outside for the weights V and C because those were actually indexed by k. But now we have a k on the right-hand side and no k on the left-hand side. To answer this question, we have to take a little detour and talk about the law of total derivatives. The law of total derivatives is like this. Suppose we know the position of an object in a three-dimensional space with respect to time. So we have x of t, y of t, and z of t, which are some arbitrary functions. By the way, these variables, x, y, z, and t, for the purpose of this slide, have nothing to do with neural networks. You can think of them as the position of a planet moving in space. Now, suppose we have some function of the position called f. The question is, what is the derivative of f with respect to time? We know that f is a function of x, y, and z, which are all in turn functions of the time t. So we know that the chain rule will apply somehow. But the answer is somewhat non-intuitive. We have to multiply the partial derivatives of f with respect to x, y, and z with the derivatives of x, y, and z with respect to the time t. Then we add them together. We can generalize this formula so that we can have any number of variables which are parameterized by t. In this case, we just sum over each of the individual terms. So how does this apply to our neural network? Well, we have our objective J. J is a function of a and k for all n's and all k's. A and k is a function of WDM. Why is that? Well, it's helpful to draw a picture of a neural network. You can see that WDM is the weight that carries one input node to one hidden node. But remember that this one hidden node influences all of the output nodes. In other words, all of the big K outputs. You can even draw it out in a picture to see the analogy between the general form of the law of total derivatives and our specific form, which applies to a neural network. On the right of these diagrams, we have the function we want to differentiate, f in the general case and j in our case. In the middle, we have all of the intermediate variables, x of k in the general case and a of nk in our case. At the input, we have the parameter, t in the general case and wdm in our case. So what does this mean for us? It means that in order to get rid of this pesky dummy variable k, we actually have to sum over all the possible values of k. So notice that we now have a double summation over the output nodes, one over k prime and another over k. Lucky for us, we've already solved the inner part of these summations, so the innermost summation goes away. We know that these combine to just give us t minus y. By the way, since we know that the derivative for the weight matrix and bias vector are very similar, we'll just focus on the weight matrix for now and ignore the bias term until the end. At this point, we have 3 derivatives to solve. Luckily, these are not very difficult since we've done them all before, well, for the most part. The derivatives of the activations are simple because they are just linear terms. So the derivative of ank with respect to znm is just vmk, and the derivative of alpha nm with respect to wdm is just xnd. The derivative of sigma will be different depending on what sigma represents, whether you use the sigmoid, the tanh, or the rel-u. Luckily, we've already found the derivative of the sigmoid when we studied logistic regression, so it's not necessary to do it from scratch again. Of course, if you don't remember how it's done, you may want to do it by hand. For the other derivatives, you're encouraged to solve them on your own if you don't know how they're derived. It's basically just Calculus 1 homework. As mentioned earlier, for the purpose of these lectures, we're going to assume that the hidden activation is a sigmoid, but you can easily plug in the other derivatives for the other activation functions. Finally, we can plug in all the derivatives we just found to arrive at our final answer. As before, for the bias term, we just replace x with 1. The next step is to vectorize these gradients for our implementation, which is not as easy as it was for the previous lectures. This is because it involves quite a few more terms, but it also involves some element-wise multiplication, which is not the same as proper matrix multiplication. We can reason about how it works if we look at the shapes of each matrix involved. First, note that the z terms are just element-wise multiplication. So every time we have znm, we have 1 minus znm, so the indices are the same. There's no mixture of indices for z. So this term just turns into z times 1 minus z, where z is the full n by m matrix of hidden layer values. Also note that the circle with a dot in it means element-wise multiplication. For convenience, we can just call this z prime for short. It helps to consider the shape of each object we have to multiply. The first, t minus y, is of shape n by k. The weight matrix V is of size m by k. The z prime term, which we just vectorized, is of size n by m. Finally, x is of shape n by d. So you can see that this is not just a straightforward matrix multiply, because none of the inner dimensions match. But here's what we can do. First, let's take the first 2 terms, t minus y and v. If we transpose v, then we get k as the inner dimension, and this is a valid matrix multiply. The result is a matrix of size n by m. And by the way, it makes sense to collapse and sum over k, because we know that in the scalar form, we are summing over k. Luckily, this matches the shape of z prime, which is also of size n by m, so we can do another element-wise matrix multiply. Lastly, we have a matrix which is of size n by m, and X which is of size n by d. We want the result to be d by m, and we know that we have the sum over n, which is exactly what matrix multiplication does. So if n is the inner dimension, that means we'll sum over it. So in fact, what we want to do here is transpose X and do a matrix multiply with the matrix we found previously. By the way, if you prefer, we can write this more generically using z prime, so that it can be the derivative of whichever hidden activation function you choose. Similarly, we can do the same thing for the bias term, but remember that there isn't really a linear algebra symbol to denote the summation over an index, so we'll just write this out in NumPy form. Again, it's just the same term we had before, except without the x, or equivalently, what we would have if x was just 1.
Hey guys, and welcome back to this class, Data Science, Deep Learning in Python, Part 1. In this lecture, we're going to show you how to do backprop in code. If you don't want to code along, you just want to look at the code or you made a mistake, go to the GitHub repo and check out backprop.py. So a lot of this stuff, I'm just going to copy and paste from the forward prop file, since they're exactly the same. So classification rate and going in the forward direction are going to be exactly the same, and the imports are going to be the same. Okay, now let's define a main function. So if name is main, then we're going to run the main function. Okay, and the main function is going to consist of creating the data. So this is very similar to before, but we have to do some extra stuff here. So I'm going to get n, which is the length of y, and then I'm going to turn the targets into an indicator variable, right? Because we expect those to be either 0 or 1, whereas in the y variable, we represent the classes by 0 to k minus 1. So we want an indicator variable of size n by k, and then for I in x range n, we're going to set t of I, yi equal to 1. So that's like a one-hot encoding for the targets. And just in case you forgot what the data looks like, we're going to do that again as well. Now the starting part of this is the same, so we're going to start by randomly initializing the weights, and then we're going to do backprop. So I'm going to set my learning rate to be 10 to the minus 7. I'm going to keep an array of the cos function so that we can plot it afterwards to see the progression. Now I'm going to do 100,000 epochs. And we're going to call forward function. Now notice this version of the forward function not only returns the output, it also returns the hidden layer. So notice how it returns z here, and that's because this is required to calculate the gradient. So every 100 epochs, we're going to calculate the cost. We haven't written this function yet, but we will. And we're also going to get the predictions. So that's argmax of the output on axis equals 1. We're going to use those to calculate the classification rate. So that takes in the targets and the predictions, and we're going to print them. And we're going to append the costs to the cost array. Okay, and now we're going to do gradient ascent. This is just the backwards of gradient descent. So it's a positive instead of a negative, and then it's t minus y instead of y minus t. Just to show you guys how you can do it both ways. So it's the learning rate times the derivative with respect to W2. That takes in the hiddens, the indicator targets, and the output. Now B2 will be learning rate times the derivative with respect to B2, and that takes in the targets and the output. W1, so remember we're going backwards, is learning rate times the derivative with respect to W1. That takes in X, the hiddens, the target, the output, and W2. And then B1 will be the learning rate times the derivative with respect to B1, which takes in the targets, the output, W2, and the hiddens. Finally, when that's all done, we can plot the costs. Alright, so now we can go ahead and define the cost function. So that takes in the targets and the outputs. We're just going to do it directly from definition. So it's the targets times the log of y, and then we return the sum. So now all that's left to do is to define the derivative functions. So let's at first do the derivative with respect to W2. Remember that takes in the hiddens, the targets, and the output. So we can get the shape NK from the targets. We can get the number of hidden units from z.shape1. Now I'm at first going to show you a slow way of doing this, and then we're going to speed it up later. So this is direct from our derivation. So ret1 is going to start out as zeros of size m by k, and then we're going to count up to n, up to m, and then up to k. Okay, and then ret1 mk is equal to t minus y, since we're doing gradient ascent, times znm. All right, and then we return ret1. Now let's do the derivative with respect to B2. So this just takes in the targets and y, and we return t minus y, and we sum along axis equals 0. Next, let's do the derivative with respect to W1. So that takes in x, the hiddens, the targets, the output, and W2. And we're going to again do this the slow way at first. So we're going to get n and d from x.shape. We're going to get m and k from W2.shape. And this is the slow version. So ret1 is equal to zeros, and it's d by m. And we're going to do some for loops. So loop up to n, loop up to k, loop up to m, and then loop up to d. Okay, so the indices are d and m, and then we're going to accumulate tnk minus ynk times w2 mk times cnm times 1 minus cnm, so that's the derivative of the sigmoid, times x nd. Okay, and once we're done that loop, we can return ret1. Now the last thing to do is the derivative with respect to b1. And that takes in the targets, the output, w2, and the hiddens. Now we're going to do this the fast way. I would encourage you to try to derive how we came up with this as homework. So you want to be able to do these vectorization operations. So that's t minus y, matrix multiplication, w2 transpose, element by element multiplication, times z times 1 minus z, and then we sum along axis equals 0. Alright, so everything here is good. Let's try to run this. So in case you forgot, this is what the data looks like. Okay, so our cost is decreasing, but it's doing so very slowly. So we don't want to use those for loops. So let's cancel this and fix our for loops. So you can tell looking at this derivative with respect to w2 that the m only shows up once on each side. So that should be pretty simple. So let's define a ret2 equal to the same size, m by k. And now let's just get rid of the for loop over m. So for n in x range n, for k in x range k. Now we're going to do this whole thing, but we're going to choose all of the m's at the same time. Right, so it's just two one-dimensional arrays on both sides. And to start, we can assert that the abs of ret1 minus ret2 is less than a very small value. So let's run this and try again, and if it works, then we'll erase this part. So this has to be ret2 also. Okay, so it's not failing, everything is still good. So now we can simplify this further. So let's get rid of this loop. And let's maybe get rid of the k's. Right, so let's create a ret3 equal to zeros of size m by k. And just loop through n. Okay, and then ret3, all of ret3. That'll be the outer product of z of n and t of n minus y of n. Okay, so we get rid of this assert, and we create a new assert. So ret2 should be very close to ret3. and we'll return ret3. All right, so everything's still working. That's great. So now we can simplify this further. We actually don't have to loop through anything. So instead of doing all that, say ret4 is equal to z transpose dot t minus y. Right, so z transpose will be m by n, t minus y will be n by k, so the result will be m by k. And we can assert that ret3 is very close to ret4. So let's run this and try it again. Okay, so everything's still working. It seems to even be working a little faster. So let's get rid of this. Let's get rid of this. Let's just return z transpose dot t minus y. Now as an exercise, I want you guys to do this at home. Figure out how we can replace this for loop by doing this code instead. So the delta at z will be t minus y dot w2 transpose times z times 1 minus z. And then we want to return x transpose dot delta z. Okay, so let's run this. Notice the great increase in speed now. All right, so this is the log likelihood. As we progress through each iteration, we probably could have gone a little bit longer. As you can see, the progression isn't quite flat yet. And we get about 97% accuracy.
Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python Part 1. Now this is where the fun begins. What happens if we want to train a neural network with an arbitrary number of hidden layers? Luckily, we can derive more general rules than what we've discovered so far. In order to help us see what these rules are, let's first try to derive the gradients for a neural network with 3 layers of weights. To recap what we've done previously, we did logistic regression, which is 1 layer, and we looked at a neural network with 2 layers of weights. So a neural network with 3 layers of weights is a natural next step. Since we're running out of letters, we're going to use superscripts to represent our layer values and our weights. So here we have 3 sets of weights, W1, B1, W2, B2, and W3, B3. We call the 2 hidden layer values Z1 and Z2, while the activations are A1, A2, and A3. You can even think of X as Z0 and Y as Z3 if you want, since it might help you follow the patterns more easily. Similarly, when we consider the size of each weight matrix, we can consider the input shape D to be M0 and the output shape K to be M3. So the size of W1 is D by M1, the size of W2 is M1 by M2, and the size of W3 is M2 by K. Or you can think of it more generally as the size of WL is m of L minus 1 by m of L. As usual, the next step is to find the gradient of our objective. Now, because these are composite functions, it makes sense to work backwards, hence the name backpropagation. This is just the same pattern we've been following all along. So first we're going to find the gradients with respect to W3 and B3. Then we're going to find the gradients with respect to W2 and B2, which of course requires more terms due to the chain rule. Finally, we're going to find the gradients with respect to W1 and B1, which will require even more terms. So here is the chain rule, which is the same as what we had before, but expressed in terms of our new variable names. Notice that the indexes also have to have superscripts because we're going to follow the convention that little m2 counts from 1 up to big M2. In other words, we're still using the lowercase letter for the index and the uppercase letter for the total size with corresponding superscripts. Importantly, despite our new notation, this does not change the answer. The three derivatives we found still work out to be the same, just with new symbols. So here are the solved gradients, which you should recognize as exactly what we had before. If you don't see why that is, then you should derive them again. As before, the next step is going to be a little more tricky because it involves more terms in the chain rule. But importantly, we've already derived these. So it's not a matter of deriving them again. It's just a matter of replacing each symbol with our new set of symbols. Also, recall that we've applied the law of total derivatives here, just like before. So we sum over k twice. One thing that's confusing about this is that there are a lot of superscripts and subscripts. So one thing you might want to do is go through each term and do a sanity check to make sure all the superscripts and subscripts make sense. For example, the indices for W2 are M1 and M2. Does this make sense? It does because we previously established that the size of W2 is big M1 by big M2. The next step, of course, is to plug in the expression for each individual derivative. And remember, we've done this already. We're just replacing the old symbols with the new symbols. As a side note, we're again assuming that we're using the sigmoid activation function. The main difference between the 3-layer neural network and the 2-layer neural network is that the last term where we previously saw x, we now see z1. The final step is to calculate the gradients for the first layer, which will be the largest number of terms in the chain rule that we've seen so far. Luckily, this is nothing more than following the same pattern we've already been following for the past few lectures. So let's start by writing out the chain rule. The most important part of this is that we have to remember the law of total derivatives once again. In particular, not only do we have to sum over k, we also have to sum over m2. Basically, you can think of this as you have to sum over any index that does not appear on the left-hand side. And since D and M1 are what appear on the left-hand side, we have to sum over every other index, which in this case are M2 and K. I've also written out all the functions here so you can easily see how they depend on one another, which tells us why each of these terms appears in the chain rule. So basically, for every function we have one derivative. And since we have 7 functions, we have 7 derivatives. Now, if you don't see how this works right away, which is forgivable since it's quite long and a lot of the symbols look similar, please go through it slowly and make sure that this indeed follows the chain rule. Each of these derivatives is just the derivative of one of these functions from the left-hand side with respect to some variable on the right-hand side. As before, we have conveniently solved most of these derivatives already. For any of the derivatives we haven't solved, they still have the same functional form of derivatives we have solved, so it's just a matter of copying the pattern rather than actually deriving them again. So please double check that what I've written here is correct. if you don't see why it works right away. Also, make sure that you know which derivatives each of these terms correspond to. Note that I've replaced the derivative of z2 and z1 with z2 prime and z1 prime in order to save space. But remember that these are just the derivatives of the activation functions. So if we use sigmoid, then it would just be z times 1 minus z, and so on. To summarize what we've done so far, we've gone from solving for the gradient of a one-layer neural network, which is logistic regression, to a two-layer neural network, and now a three-layer neural network. Here in this page, I've summarized the derivatives for each layer of a three-layer neural network. As a side note, sometimes people disagree on exactly how to count the layers. For example, if you have two sets of weights, then you have three data layers, meaning x, y, and z for the hidden layer. But for the purpose of this course, when we count a layer, we're counting it as how many linear transformations do we do? In other words, how many weight matrices and bias vectors we have. Since we have three sets of weight matrices and bias vectors, we call that a three-layer neural network. At this point, it's important to consider what patterns we've learned to see so far. The easiest pattern to see is a matter of counting. I just described on the previous slide that we had 7 functions and we also had 7 derivatives. For the weights we looked at before that, we had 5 functions and 5 derivatives. And before that, at the output layer, we had 3 functions and 3 derivatives. So it would appear that every time we go back one layer, we had 2 functions and 2 derivatives. That makes sense because at each layer, we add 2 more functions. The first function is a linear transformation on the input to that layer to get the activation, and the second function is the application of the activation function. The next pattern we want to notice is that the further and further we go back, the more common terms we encounter, meaning terms we already calculated previously. That should tell us something. It tells us that this calculation is recursive. In other words, we can use the results of previous calculations without recalculating them. It helps to look only at the weight matrix gradients to help see the pattern. As you can see, the first part of the weight update for W3 appears in the gradient for W2. An even bigger part of the gradient for W2 appears in the gradient for W1. Here's another pattern we notice. If we look at the vectorized forms of the update equations for the one-layer neural network and the two-layer neural network, we can see that they look very similar. And in fact, if you look a little more closely, it seems we always follow the same pattern. For a general W at layer L, its gradient is the input data matrix into that layer multiplied by some other term. Let's just call it delta for convenience. Now, recognizing that this is the pattern, let's try to reason about what the shape of everything has to be. Starting from the weight matrix WL, this has to be of shape m of L minus 1 by m of L, which we've already established. We also know that z of L minus 1 is of shape n by m of L minus 1. And therefore, we know that this delta term, whatever it may be, must be of shape n by m of L. This is just to satisfy the rules of matrix multiplication. Let's now look back at our equations for the gradients of the 3 weight matrices to see what this delta variable should actually be. The first delta at the output layer seems a little different from the others, but that's only because the output layer involves a softmax and then the cross-entropy loss function, which the other layers do not. In this case, we can say that delta 3 of nk is equal to tnk minus ynk. The second delta must be everything up to the input to that layer, meaning up to z1. Importantly, notice that z1 does not depend on k, and therefore we can include that summation over k in our expression for delta 2, which should be of size n by m2. The last delta, the delta at the input, or delta 1, can be found similarly by taking everything except the final x term. You notice that we also sum over m2 because x is not indexed by m2, nor is delta 1 indexed by m2. So we're just following the same rule as before, which is to sum over any of the indices that don't show up outside the summation. What's interesting about this is that once you define delta, it's easy to see that each delta can be defined in terms of the deltas that came ahead of it in the neural network. So delta 2 contains the expression for delta 3, and delta 1 contains the expression for delta 2. Using this idea, we can actually express each delta in terms of the delta we found previously. Of course, the only delta we can't do this with is delta 3, since that's at the head of the neural network and is different from all the others. If you think of this in terms of recursion, that would be our base case. So here we can see each delta defined in terms of the delta that came before it. And from here, it's easy to see that every delta, except the very first delta at the head of the neural network, follows a recursive pattern. If we say that we have a big L layer neural network, then we can define delta of big L as t of nk minus y of nk. And then we can define all the subsequent deltas from big L minus 1 down to 1 using the recursive expression you see here. As usual, we can also vectorize this expression for delta. So you might want to double check on paper that all the dimensions make sense. At this point, our weight updates become very simple, as you can see here. Again, since there's no conventional linear algebra notation for the sum over an axis, we use NumPy notation to make things more clear. Although, it's equivalent to multiplying by a vector of length n that just contains all ones. One thing I want to point out in this lecture is that most other resources teach this topic backwards. I discussed this more in my lecture, The Wrong Way to Learn Backpropagation. In particular, what they do is they start with the result, and then sometimes explain how they got there. Or worse, they don't explain it at all, which is very unfortunate, and is actually most often the case. Because what this leads to is people thinking that backpropagation is some kind of magical algorithm that came out of nowhere, but happens to work very well, when that is clearly not the case. And therefore, what we've done is shown that backpropagation is nothing but gradient descent. And not only that, but by recognizing the recursive nature of the gradient equations, we can do some simple substitutions that make finding the gradients very easy. All we needed to do was recognize the common pieces in each gradient and assign that to a new recursively defined variable called delta. Let's summarize what we just did since it was extremely long. This lecture is the culmination of all the knowledge we've gained from the previous lectures in this section. While the derivation and subsequent update equations were initially extremely complicated, you can see that in the end we actually end up with just a set of a few simple rules. At each layer, we first define a delta term, which is a recursive equation in terms of the delta we previously found. Then our weight gradient is just the input to that layer multiplied by the delta term. Once we find the weight gradient, we perform gradient descent as usual. And so now you know why this algorithm is called backpropagation. It's because we work backwards by finding the delta at each layer in terms of the delta at the layer ahead of it, and then multiply by that layer's input to get the gradient.
Hey guys, and welcome back to this class, Data Science, Deep Learning in Python, Part 1. In this lecture, I'm going to look at backpropagation from another perspective. This is how you see backpropagation taught in pretty much every other course except this one. And in this lecture, I'm going to explain to you why it's the wrong approach. A lot of people come into deep learning because they think deep learning is a powerful tool they would like to know about, but they are averse to math. They think they are going to learn this cool new thing, but then I tell you, well, this isn't really that cool. It's just the chain rule from first year undergraduate calculus. So if you find that unnerving, or if your brain immediately turns off at the sight of math, you probably want to reevaluate why you want to learn about deep learning, because it's actually all math. So let's get into the typical approach to backpropagation. First, we start with this term called delta, which we can think of as the error at a node. So therein lies the first problem. Why is this the error? Why is it not some other expression? So it's not very well defined. Then we say the weight update can be expressed in terms of this error. Well, that makes sense, that the update should depend on the error at a node that is affected by that weight. But again, where does this expression come from? We can't just go around making things up because they make sense when you explain it in words. Now the next part is the actual backpropagation part. We show that the error propagates backward by showing that the delta at the previous layer depends on the delta at the next layer. But again, why should this be? You can't just make things up because they sound nice. So the answer here is this is actually the opposite of what you should do when you're trying to understand backpropagation. Here are the basic facts. We know we're trying to maximize the likelihood, or equivalently, minimize the negative log likelihood. The name of it doesn't matter, we're just trying to minimize something. We know that gradient descent is a general all-purpose method that works to optimize any function. We've already done this hands-on with both logistic regression and with a quadratic equation. Everyone knows the quadratic equation because that's just high school math. So we have a thing we want to optimize. We already know how to do that. We just do gradient descent. So that's the right approach. Not defining deltas for no reason. Not defining deltas in terms of other deltas for no reason. Now the delta is actually very useful because it allows us to define backpropagation recursively. Each layer's update depends only on the layer in front of it. The key is, we're already exposed to this pattern by taking the gradient ourselves. And that's the way the delta should be defined. You want to first take the right approach. Then you look at what you found, realize that there is a pattern, and then make substitutions so that the pattern becomes more obvious and more simple. So to summarize this, the wrong approach is to just define the delta for no reason, and just know in the back of your head that you took the derivative of the cost function. The right approach is actually being able to take the derivative of the cost function, doing it clearly enough so that you see and understand the pattern that emerges from it, and then make substitutions to make the pattern more clear.